Hi, today we will be discussing Lab 3 of Physics 2212, Magnetic Field of a Bar Magnet. In this experiment, we will explore how magnetic fields change based on the distance between the source and observation location. We will also model and visualize the magnetic field of a dipole after determining its dipole moment from experimental data. An important observation from this lab is that the magnetic field strength increases as the distance decreases. The first part of this lab involves finding the on-axis distance that produces a certain magnetic field. The setup is shown on the left. The second part of this lab is similar but finds the magnetic field 45 degrees off-axis as seen on the right. First, we'll go over some important physics principles. The magnitude of the magnetic field of a dipole on axis is approximately mu naught over 4 pi times 2 mu over r cubed. The magnitude of the magnetic field of a bar magnet is kr to the n, where k is a combination of constants and other parameters, and n is the distance dependence value. Taking the natural log of this equation allows it to be plotted linearly and gives an equation in the form of y equals mx plus b. The last equation shown will be used in the glow script model to visualize the magnetic field of a dipole. Here are the data and results from the first part of the experiment. We observed that when a magnet is far away from the magnetometer, it measures a near zero magnetic field in the x direction. As the magnet moves closer, the measured magnetic field increases in the x direction. The table shows average distances between the magnet and the magnetometer to yield various x components of the magnetic field. The natural log of this data is plotted on the graph with the line of best fit. We can find n and k by looking at the line of best fit, where the y-intercept corresponds to the ln of k, which is negative 14.191. Solving for k gives a value of 6.87 times 10 to the negative 7th. The slope corresponds to the distance dependence value n, which is negative 2.8548. We can also find the magnetic dipole moment by making some approximations. The distance dependence value n is about negative 3, which would make the magnitude of the magnetic field of a bar magnet k over r cubed. Therefore, it can be set approximately equal to the magnitude of the magnetic field of a dipole on axis. Plugging in k and solving for mu gives a value of 3.43. These are the data and results for when the dipole is 45 degrees off axis at an average distance of 0.254 meters. The magnetic field at this location, ignoring the z component, is negative 8.66 times 10 to the negative 6th, 3.82 times 10 to the negative 5th, 0 teslas. We account for Earth's magnetic field by subtracting it from the y component. To visualize the magnetic field produced by the magnet, this model was coded using GlowScript. The model is shown on the left and the calculation results are shown on the right. This model has magnetic field vectors at various locations around the dipole. 2 orange arrows represent the field on axis, the 4 cyan arrows represent the field perpendicular, and the pink arrow is the 45-degree off-axis field. To see the full code for this model, go to the link in the description. This equation gives the magnetic field of a dipole in terms of the dipole moment and r hat. It is modeled by the dipole B function shown here to calculate the magnetic field vector for each of the arrows. Here's the code that creates the arrows and displays the calculated magnetic field vector at various locations. The last 4 lines are repeated for each arrow in the model. This code is for the off-axis arrow and is very similar to the previous slide, but uses the perpendicular distance. The theoretical field measured 45 degrees off-axis is not the exact same as the experimental field. Reasons for this may include that other magnetic objects and electronics in the surrounding area caused interference. Also, the magnetometer may have been misaligned, causing misreadings. If the experiment did not compensate for magnetic north, and the x and y components of the measured magnetic field would have been different based on the angle to magnetic north. If two magnets were used, they would act as one larger magnet, which would increase the magnetic field and therefore decrease the measured distances. Thank you.